Welcome to the lecture series of Basic Electrical Engineering. The subject code is ECE 101. The topic of today's lecture video is Elementary Theory of an Ideal Transformer and EMF Equation of Transformer. So first of all, we will discuss elementary theory of an ideal transformer. This figure shows an ideal transformer in which we are having the voltage, applied voltage V1, induced EMF E1, the number of turns on the primary side are N1, this is the flux produced phi, N2 is the number of turns on the secondary side, E2 is the induced voltage, and V2 is the voltage on the secondary side. So, according to the definition, an ideal transformer is one which has no losses, that is, its windings have no ohmic resistance, there is no magnetic leakage, and hence which has no I square R and core losses, means that it is not having any type of losses in the ideal transformer. So, if we consider an ideal transformer as shown in figure whose secondary is open and whose primary is connecting to sinusoidal alternating voltage V1, this potential difference causes alternating current to flow in the primary. The function of this current is merely to magnetize the core. It is small in magnitude and lags V1 by 90 degree. The current induced in the primary side, that is IM current, is lagging the voltage V1 by 90 degree. This alternating current IM produces an alternating flux. This here the current IM is produced, which produces the alternating flux phi, which is at all times proportional to the current, means it is directly proportional to the current, and hence it is in phase with it. As shown in this figure, this is a phasor diagram of an ideal transformer. Here IM is in phase with phi and IM lags behind V1 by 90 degree. This is the induced voltage E2 and E1 is opposite to that of V1. So this is the phasor diagram. Then working principle of an ideal transformer. An ideal transformer is perfectly coupled lossless transformer with infinite high core magnetic permeability. It is purely an imaginary transformer. In actual practice, ideal transformer doesn't exist. Whatever we are studying here in this topic, this is all imaginary. But we consider this in our work so that on the basis of these ideal transformers, the practical transforms are formed or produced. So, it is purely an imaginary transformer which has many similar properties related to the practical transformer, and it is only used for study purposes because it is not in actual practice. This is imaginary, so it is considered only for the study purposes. The energy in an ideal transformer is completely utilized, that is, its efficiency is exactly 100%. This shows the diagram and the phasor diagram of an ideal transformer. As I have told you earlier that we are giving the AC supply, alternating supply, V1 IM current is magnetizing current which is produced on the primary side, E1 is the magnetizing EMF voltage, and these are the number of primary windings. Because of this IM, this flux phi is produced, and N2 is the number of windings on the secondary side, and E2 is the induced voltage, and this is the V2. So IM and phi are in phase with each other, and V1 is leading IM by 90 degree, E1 is opposite to that of V1, and E2, this is E2 and V2 are on the lower side. So the changing flux is linked both with the primary and the secondary winding. The change in flux is here. Therefore, it produces self-induced EMF in the primary. This E1 is the self-induced EMF in the primary. This self-induced EMF E1 is at every instant equals to and in opposite to V1. That is why we are considering here on the lower side, V1 on the positive side and E2 on the negative side. It is known as counter EMF or back EMF in the primary. So self-induced EMF E1 is also known as back EMF. Similarly, there is produced in the secondary an induced EMF E2, which is known as mutually induced EMF. The EMF induced here E2 is called mutually induced EMF, and it is here on the negative side. E1 lags IM by 90 degree. So this is IM and EM lags by 90 degree. Here V1 leads phi by 90 degree. This is flux. The instantaneous value of applied voltage, induced EMF, flux and magnetizing current are shown in figure. All the values considered here, V1, E1, N1, N2, E2, V2 are shown here in this diagram. So, above mentioned properties are not possible in the practical transformer. In an ideal transformer, there is no power loss. Therefore, the output power is equal to the input power, because we are saying in the definition that there is no losses. So output power is equal to input power. So we can say that E2 I2 cos phi is equals to E1 I1 cos phi, or we can write it as E2 I2 is equals to E1 I1, or we can write it as E2 upon E1 is equals to I1 upon I2. Since we know that E2 is directly proportional to N2, higher the values of N2 is the number of secondary windings, the higher is mutually induced EMF. Then similarly E1 is directly proportional to N1. Also E1 is similar to V1. V1 is the applied voltage and E2 is similar to V2. So therefore transformation ratio, this ratio E2 upon E1 or I1 upon I2 is called the transformation ratio. So transformation ratio will be given by the equation V2 upon I1 is equals to E2 upon E1 is equals to N2 upon N1 is equals to I1 upon I2 is equals to K. So these are called transformation ratios. The primary and secondary currents are inversely proportional to their respective turns. Here you can see that this is V2, E2, N2, but here in the case of current it is I1. Now we are talking about the next topic, EMF equation of a transformer. N1 is the number of turns in primary, N2 is the number of turns in the secondary, phi m is the maximum flux in core in Webers, and it is also given by Bm into A, and Bm is the flux density into area, and F is the frequency of AC input in Hertz. As shown in figure, flux increases from its zero value to the maximum value phi m in 1 quarter. Means this is a complete cycle, one complete cycle, and this is 1 quarter, and it increases from 0 to 5. So this 5 m is the maximum. So it increases, it shows maximum flux in the first quarter, means half quarter. 1/4 frequency shows that the maximum flux. So we can write it as 1/4 of the cycle, that is in 1/4 f seconds. So average rate of change of flux is 5m upon 5m is the maximum flux upon 1/4 f, or it can be written as 4 f 5m Weber per second or volts. Now the rate of change of flux per turn means induced EMF in volts. So average EMF turns is given by 4f5m. If flux phi varies sinusoidally, then RMS value of induced EMF is obtained by multiplying the average value with the form factor. As we know, form factor is equals to RMS value upon average value, and it is given by 1.11. So when we multiply it with the factor, so RMS value of EMF per turn is equals to 1.11 into 4 f5m. Then the equation will become 4.44 f5m volts. So this is how we get this EMF value. Now RMS value of the induced EMF in the whole of the primary winding. When we are talking about the EMF value on the primary side, it is induced is equals to induced EMF per turn into the number of primary windings. So it will become E1 is equals to 4.44 f, N1 is the primary turns, and 5m is the maximum flux. And we can replace this 5m by Bm into A. Bm is the flux density and A is the area. Similarly, RMS value of the induced EMF in the secondary side, it is same, but we are taking the secondary winding N2. It is seen from equation 1 and 2. If we compare this equation 1 and 2, E1 upon N1 is equals to E2 upon N1 is equals to 4.44 f5m. This is equation 3rd. It means that EMF turns in the same in both the primary and secondary winding. In an ideal transformer on no load, when we are talking about this transformer, when there is no load on the secondary side, then V1 is equals to E1 and V2 is equals to E2, where V2 is the secondary terminal voltage, the voltage produced on the secondary terminals. Then voltage transformation ratio, as we talked in this equation, E1 upon N1 is equals to E2 upon N2. So voltage transformation ratio E2 upon E1 is equals to N2 upon N1 is equals to 4.44 f5m is equals to K. This K is called the voltage transformation ratio. If N2 greater than N1, that is K greater than 1, then transformer is called step up transformer. If N2 is less than N1, that is K is less than 1, then transformer is called step down transformer. Again, for ideal transformer, input volts per ampere means input power is equals to output power. That can be written as V1 I1 is equals to V2 I2, or we can say I2 upon I1 is equals to V1 upon V2 is equals to N1 upon N2 is equals to 1 upon K. This is called inverse ratio of voltage transformation, because here we are talking 1 upon K. A voltage transformation is represented by K, and when it is 1 upon K, then it is called inverse ratio of voltage transformation. And this is all about your this lecture. Hope you like this video. Thank you so much.